All right, let's take a look at section 5.2. Okay. So in this section, we're still working with a probability distribution like we talked about last time, but this is the one we really want. Okay. Everything we talked about in 5.1 is just kind of general, applies to any kind of probability distribution, but we're going to look at a special case of a probability distribution in 5.2 called the binomial distribution. All right, so first thing we got to do, we got to talk about what makes a probability distribution a binomial distribution. Okay, what makes it fall into this category? We've got several things here. It's not a big deal. Okay? But we've got several things here. So first of all, the name is binomial. So what does bi mean when we're using it as a prefix normally? Two, like a bicycle. It has two wheels. So this is the main thing, is if we're doing a probability experiment that only has two possible outcomes, then there's a good chance that it's binomial. Okay? So we're dealing with discrete data, okay? And we have a fixed number of independent trials. We'll talk about all that in a little bit more of a second, but the main thing is that we only have two possible outcomes. All right, so if we have these, we're going to have 6 properties. Okay? If we got all 6 of these things, then we're dealing with a binomial distribution. Okay? So number 1 here says our experiment has a fixed number of identical trials. Okay? So that means whatever experiment we're doing, we're not going to let it go on to forever. Okay? We have some fixed number. And then it also gives you a symbol we can use here. It says whatever number of trials we have, we're calling that n. You can think about it like sample size, like we have been thinking about it. That's okay. We want all the trials to be identical. Okay? We don't want to change anything between experiments. Number 2 is a little trickier to explain since we skipped the probability chapter, but number 2 says each trial is independent of the others. So what that means is that when we do the experiment once, it doesn't have an influence on the outcome the next time we do the experiment. We want them to be independent. So a good example of that is like when we were thinking about flipping coins. If you flip a coin and get heads or tails on one trial, it doesn't have an effect on whether or not you get heads or tails the next time. Right? The next time it's still 50-50. Something that would be dependent, so something that would be not what we want, it would be like drawing cards out of a deck of cards. If you draw a card out and then you don't put it back, then the next time you draw a card, it's changed the numbers, right? You don't have as many cards in the deck that time, so it would have an influence on the probability the next time. We don't want that. We want independent events. Okay? All right, and number 3 is the big one. It says for each trial, we only have 2 possible outcomes. Okay? And we're going to call one outcome a success and the other outcome a failure. It doesn't mean one is good, one is bad. It's just how we keep up with counting things. Okay? So whichever event we're counting, we call a success. And then the other one we would call a failure. Okay? Again, doesn't mean good or bad. Okay? Come here. Okay? Doesn't mean good or bad. Okay? Got those 3? All right. And these slides are on Canvas too. Okay. All right. Number 4, the top part says the same thing. I had it all crammed into one slide, so I just made 2 so we could actually read it. Okay. Number 4 says for each trial, the probability of getting a success we call P. Okay. So whatever event we're counting, the one that we call a success, we call the probability of getting that event P. And then the probability of failure is 1 minus p. And that just turns out that way because if we only have 2 events and we're adding the probabilities together, we have to end up with 1, right? A total of 100% probability. So P's probability of success, 1 minus P's probability of failure. Okay. Number 5 is our random variable. If we're working with a binomial, our random variable keeps track of how many successes we have in n trials. Okay? So however many times we're going to do the experiment. X is going to count how many successes we had. Okay. And then the last one gives us 2 formulas we can use for the binomial distribution. Okay, so I'll write these up toward the top so you can see them better, especially if you're in the back. So the first one says the mean of a binomial distribution is just n times p. N's the number of trials, P's the probability of success. We just multiply those together and get the mean. Okay. That's a lot easier than in the last section. Right, we had, on the last section, if we wanted the mean or the expected value, we had to take each outcome, multiply it by its probability, and add all those up. Okay. With a binomial, it's much easier. It's just n times p, and we're done. Okay. And then the bottom one gives us variance. We are really going to want standard deviation most of the time. So for standard deviation, it's the square root of n times p times 1 minus p. Okay. So we want the standard deviation of one of these distributions. We figure out how many trials we're doing, that's n. Figure out the probability of success, that's p, and then do 1 minus the probability of success, get 1 minus p. And we just multiply those 3 numbers and take the square root. So much easier than the last section again. Okay. And then don't forget, I mentioned it in passing, but don't forget when we're talking about the mean and we're dealing with probability distributions, the mean is the same thing as the expected value. So expected value and mean mean the same thing for a probability distribution. All right, so let's look at the little problem here. We'll use our 2 formulas. They're easy, so we don't have to practice them a whole lot. Here's one. It says, consider the experiment of tossing a fair coin 58 times. Part A says, how many times can we expect to get heads? So how many times can we expect? So it's asking for expected value. We want expected value, or that's the same thing as the mean. That's on A. Yes. And it is binomial. Okay, we only have 2 possibilities. We're tossing a fair coin. We either get heads or tails. We're doing it a fixed number of times, 58. We're not going to do it forever. The events are independent. We already talked about flipping a coin has no effect on the outcome the next time you flip a coin. So we use our formula off the last slide. It's just going to be n times p. So n is the number of trials, how many times we're doing our experiment. So what's n going to be on this one? 58, yeah, because we're flipping their coin 58 times, so n's 58. And then p is our probability of success, but you have to be a little careful thinking about this. First of all, what are we calling a success? What event are we interested in? Heads or tails? Heads, because it asks us how many times can we expect to get heads. So that's the one we're going to call a success, is heads. Tails we'll call a failure. Okay. So Then the other thing we have to be a little careful of, we're not trying to do like some complex calculation here to figure out, the probability of getting a bunch of heads or anything. All we have to think about for P is if we do an experiment one time. Okay, so if we flip a coin one time, what's the probability we get heads? 50%, right? Heads or tails, so it's 50-50 each way. So our P here is 50%, or as a decimal, that's 0.5. Okay. So what was that? 29. 0.5 times 58. Okay. That's it on that one. Our expected value, we expect if we flip a fair coin 58 times, we would expect to get about 29 heads. Questions on that one? Yes. You can leave a decimal, so if it would be like 0.5, like that, like if it came out like 28.5, yeah, you leave it 28.5, that's fine. And if it was like some long decimal, it would tell you how to round. No worries there. Okay, other ones? Okay. B says calculate the standard deviation. Normally that's one you like groan about, standard deviation, but it's easy with binomial distribution. Okay. Our formula said if we want standard deviation, the square root of n times p times 1 minus p. We've already figured out the two numbers we need, n and p. We just plug in, so n is 58. Whoops, sorry. N is 58. P is 0.5. 1 minus p, we would do 1 minus 0.5, which is 0.5. So we do 58 times 0.5 times 0.5, and then we take the square root. On this one, it doesn't tell us how to round here, so I'm just going to round to 2 decimal places. That one comes out to like 3.81. There's our mean, our expected value, and our standard deviation. Okay. They're nice, easy formulas when we're dealing with a binomial distribution. Huh? Oh, and then, yeah, we might as well interpret, right? It says, what does it tell us? So remember, this is how spread out our data is. And so we expect if we do this experiment 58 times, we're going to get about 29 heads. Okay, that's our expected value. But now it's a little weird. We're thinking about if we did the experiment 58 times, and then did the experiment 58 more times, and then did it 58 more times, then we're not going to always get exactly 29 heads. But what we could expect, looking at our standard deviation, is typically we would get 29, plus or minus 3.81, right? It'd be somewhere in that plus or minus 1 standard deviation range is what we could expect there. So it would be normal for this to fluctuate by about 4, one way or the other. So between 25 and 33. It's the same idea as standard deviation. Okay. All right. The next thing we want to do in this section is we want to be able to take one of these binomial distributions and use it to come up with probability. Okay. There's a few methods we can use to do that. The main one I'm going to do in class today is we're just going to look the number up in the table. Okay. You can also use a formula. We'll look at the formula, but you can use it if you prefer it. Okay, but you don't have to. You can just look. I'll give you the tables on test day that you need. and they're in Hawks. Okay. And then you can also, if you have a graphing calculator, you can also get the probabilities out of your graphing calculator. So they're all about the same difficulty. So we'll just mostly use a table today, and the instructions for using the graphing calculator, and I think on most of the problems, the formula too is in there. Actually, the formula is a little bit more of a hassle on some types of the problems than the calculator or using a table. Okay. So before we do that, when we're calculating probabilities here, oops, sorry, where's my, here. I got out of order in my brain here. Okay. When we're calculating probabilities, and this goes not just in this section, but in the rest of the class too, our standard is going to be to round to 4 decimal places. If you're using the formula or your calculator, it'll probably be more precise than that. But when we're using the paper tables or the tables in Hawks, they're going to be rounded to 4 decimal places. So usually that's good enough. Okay. That's going to be our habit. Okay. All right, so let's look at the formula briefly. And again, you don't have to use this formula if you don't want to. All right, but it tells us, and it gives us some definitions. Okay. It tells us if we have a binomial variable, okay, then we can figure out the probability of getting some X number of successes in N trials, okay, by using this formula. So X is how many successes we're looking for. N is how many trials we're doing, how many times we're going to do the experiment. And then P is our probability of success on if we just do one trial. It's like with flipping the coin, that was the 50%. So the formula is not bad. It looks kind of scary, but it's not bad. The thing that might make it look kind of scary is this part. This thing is, it's a probability function. I think it's called combinations. Well, it has a C on there. If you might take MS 110. A few of you, okay, so you might have done these in there, may not have, but as far as this class, all we care about it is that it's a button on the calculator. Okay? So you would just do like whatever this number is, then that button, and then whatever that number is. It's not hard. Okay, you just have to find where the button's at on the calculator. And then this part's just an exponent. This part we subtract and have an exponent. It's not bad. Okay? So you can plug your numbers in that way, get a probability. Okay? The way we're going to do them together in class today, again, is we're just going to look them up in the table. Maybe you can use the formula. Feel free to use it if you prefer that. Okay? And I've got the directions in the slides, and they're in Hawks. Okay, if you want to do it the formula way. Okay, nothing wrong with that. Okay, so there's that. Let's look at a problem. Okay. Want to find the probability here. So this one says, what's the probability of getting exactly 6 heads in 10 coin tosses? So this is binomial. We've only got 2 possibilities if we flip a coin, heads or tails. If we have a fixed number of trials, we're going to do 10 tosses. Okay? And then again, the events are independent, so it does fit our requirements for being binomial. So no matter what method you use to find these probabilities, you're going to need those 3 numbers we saw. You're going to need N, T, and X, okay, for all these binomial probabilities, no matter what method you use. Okay? So that's where we're going to start. We're going to start picking out those 3 numbers in this one. Okay? N, P, and X. Okay, so N is the number of trials we're doing, the number of times we're going to do our experiment. So what's N going to be on this one? 10. We're doing 10 coin tosses, so N is 10. Okay. All right, and then our event we're flipping the coin, and what are we going to call a success here, heads or tails? Heads, yeah, just because that's the part it's asking us about. It says, what's the probability of getting exactly 6 heads? So that's the one we want to count. So we're just thinking about if we just flip one coin, if we just do our experiment one time, what's the probability of success? What's the probability of getting heads? And again, it's 0.5. Okay, I know that's getting old thinking about the coin, so it's just 0.5, 50%. Okay. And then x, little x, okay, is the number of successes that we're looking for. Okay. Yeah, and it's 6 because it asks us what's the probability of getting exactly 6 heads. So that's going to be x. It's going to be 6. Okay. So if you wanted to, you could do this one with the formula. We would take everywhere there was an n, we plug in 10. Everywhere there's a p, we plug in 0.5. Everywhere there's an x, we plug in 6. That's what they do here. Okay, you can look over it if that's what you want to do. It's really not bad. They show this step. You don't even have to do that step in the calculator. You just punch in 10 C6 once you find the button. It's not bad. You'll get an answer done there. Okay. What I want us to think about doing, though, is using the table. Okay. So we have tables in Hawks, and then I'll give you the pages you need out of the tables on test day. Just called the binomial probability table. Okay. So let me show you where those are in Hawks. In the tables, we just use our n, p, and x to look up the right number and get the right probability. So look at one here. Okay, so just here where it's got the button that says tables, click on it. It's going to give you a bunch of choices. The one we want is just at the top, binomial probabilities. And when you click on that binomial probabilities, it's going to get you to choose the value you want for n. Let me see if I can zoom in here. It's going to get you to choose the value you want for n. So for us on this problem, we need an n of 10. And we're doing our experiment 10 times. N of 10. Okay. And then across the top, it gives you values for p. We had a p of 0.5. We're going to look down that column. And then down the left side, it gives you values for x. So we wanted, what was it, 6 successes? We wanted 6 successes. So we'll go to the row for 6. And on that one, I know it's small up here, but we get 0.2051. That's our probability. So we just find where all of our numbers cross. Okay. 0.2051 there. Okay. So just using the table. Okay. From the binomial table. Again, if you want to use the formula, you'll get the same thing. Do it either way. Just with the formula, well, I didn't even show, but you have a lot more decimal places and you just have to round to four places. That's the only difference there. And then thinking about the number, okay, interpreting, that's the decimal version, but remember we can change it to a percentage to think about it. It's usually easier to think about it that way. So what's the probability of getting exactly 6 heads? If we flip a coin 10 times, it's a little bit more than 20%, 20.51%. Questions on that one? Okay, you saw where the table was and all that good stuff. Okay. Let's do another one. All right, different setup. We're away from coins now. It says, what's the probability of rolling a die 10 times and obtaining odd digits on 8 of the rolls? So we're thinking a 6-sided die here, just the normal one. Okay. This one is binomial. I think that's maybe a little strange to think about because we got 6 choices of what we roll on a die. But here we're just looking at whether or not we get an odd digit or an even digit. So we only have 2 choices, so it is binomial. So if we want this probability, no matter what method we're using, we need NP and X. So N's our number of trials. How many times are we going to roll the dice here? Yes, okay, 10. I misread, so yeah, 10 times. Okay. Probability of success, we have to maybe think a little harder on this one. So how many odd digits do we have on a die? It's 6-sided, so we have 1, 3, and 5 on there. All right, so 3 odd digits out of 6 total possibilities. And as a decimal, it is 0.5 again. Okay, all these are not going to be 0.5, but okay, this one is. And then how many successes are we looking for? Looking for 8, and we're calling an odd digit a success here. All right, so we're looking for 8 successes. 8 successes. So you can plug into the formula here. Could put it in graphing calculator. I'm just going to go to the table again. Okay. So N of 10. So I have to change over there on the left. I want an N of 10. P was 0.5 again, so we'll go to the 0.5 column. And this time we want 8 successes, so I'll go to an X of 8. Okay. And I know it's small, but get a probability of 0.0439 on that one. So 0.0439. Questions on doing those? The hardest part on those is making sure you get NP and X right. Not bad. Okay. All right. Oh, I had this table in the slide this time. I forgot I had it this time. So N of 10, P of 0.5, X of 8, get 0.0439. All right. Okay, let's look at another one. This one's a little different. Okay, we got to step it up just a little bit. No, this one's not different. It's the same thing. Okay, one more. This is basically the same way. It's just a different problem. The next one's a different one. Sorry. Okay, so we've got a quality control expert. Estimates 10% of all batteries produced are defective. He takes a random sample of 15 batteries. What's the probability that exactly 2 are defective? It is binomial. A battery is either good or it's bad. So we need NP and X. What's our N on this one? 15, yeah, we're going to sample 15 batteries. So N is 15. here for P, we don't have to calculate anything, it just tells us. It says it estimates that 10% of all the batteries produced are defective. So we expect if we just pick one random battery, there's a 10% chance it's defective. Remember, P's probability of success, so this is a little weird. We're calling a defective battery a success. Remember, success just means that's the one we're counting. It doesn't mean it's good or bad. Okay? So probability of success or probability of a defective battery here is 10% or 0.1. And then we want to know the probability that exactly 2 are defective, so we want X to equal 2. So again, you can use formula, you can use calculus. Yes, ma'am.
On the test, if there's a question like this, and like let's say we get a decimal, like from the table, are you gonna want us to leave it as a decimal or change it to a percent?
Like for the probability? Oh yeah, you can leave it as a decimal. That's
Okay.
fine. Yeah, you can leave it as a decimal. Okay. All right, so I'm going to go to the table again, but you could use a formula or calculator is fine. On test day, the only thing I'll remind you too, but just every once in a while, the last digit is just a little bit different if you use a calculator versus the table. So I'll just remind you to like tell me if you just put it in your calculator, okay? Just so I know which way you did. Yes, ma'am. Yeah, I'll give you whatever pages you need out of it. I would, instead of saying like print them off, because you have a different table for every N, so there's like a bunch of them. If you go to the textbook, the back, you got like a stack of pages that you have to flip through in the back of the book. So I'll give you just the pages you need. Yeah, on test day. Okay, so we'll go to the binomial table again. Okay, we'll be pros at this, but this one. Okay, so go to the binomial table. Oh, wrong button. Got an N of 15. P of 0.1, so we'll leave that where it is. And then we wanted, what do we want? Exactly 2 batteries being defective, so that's X of 2. Here our probability is 0.2669. So 0.266. All right, any questions? Think you got a feel for them? Yeah, those are not bad. Okay. All right, so now we can look at one that's a little bit different. Okay. And again, if you have a graphic calculator, then if you have a TI graphic calculator, the instructions are in here, so I just left them in case you want to use them. You don't have to have a graphic calculator though. Look at this one. This one's just a little bit different. So same setup. We're estimating 10% of all batteries are defective. We're taking a random sample of 15 batteries, but the question's different on this one. It says, what's the probability that no more than 2 are defective? The last one asks us, what's the probability that exactly 2 are defective? So here, no more than 2, what does that mean? That means, 0, 1, or 2. Right? So we've really got 3 situations we're thinking about. Right? Because we're thinking about, well, we could take it and get no defective batteries, or 1 defective battery, or 2 defective batteries, and we need to know the probability of all those together. There is a long way of doing this problem, and if you use the formula, that's what you get stuck with doing. If you're using the formula on this one, you would have to use an X of 0, an X of 1, and an x of 2 and add all those answers together. So here our n was 15 still, p was 0.1, and then you would have to do the formula with 0, 1, and 2 for x and add all those answers together. Nothing wrong with doing it that way. It can get long though, because what if it asks us what's the probability no more than 14 are defective? Then you gotta do 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14, and add all those together. Nobody wants to do that. Okay. So we've got a shortcut. You remember when we were talking about frequency, we had an idea in there called cumulative frequency. And that meant that we take the frequency of whatever row we're looking at and add up the frequency of all the ones that came before it. We have the same idea with probability. We can look at cumulative probability. So what we're going to do is we're going to look up a cumulative probability for 2, and that's going to give us the probability for 2 plus 1 plus 0. It's already added together for us. Okay. So if you have a range of values like this, you don't just want exactly one number. If you have a range of values, you're going to want to use the cumulative binomial table. It's just a different table. Okay. Or if you're using a graphing calculator, it's a different function in it. Okay. If you're using the formula, then you're just kind of out of luck on this one. You just have to do extra work. But we'll go and look at the other table here. So first choice is just the standard binomial table. Second choice is the cumulative binomial. So since we're looking for a range of values, we're going to use the cumulative table this time. Okay. And the cumulative table, I should note this down, okay, gives us the probability that x is less than or equal to some number. That's what we want on this one. We want our x to be less than or equal to 2, right? 2, 1, or 0. Okay. So we're going to go to n of 15, p of 0.1, and we're going to look up 2, and because that's going to give us 2, 1, and 0 added together. Okay. So cumulative binomial table, n of 15, p of 0.1. This time we're going to look at 2. And our probability there is 0.8159. You don't have to add anything. It's already added because we're in the cumulative table. Okay. So our total cumulative probability that we want is 0.8159. Just get it out of there. Okay. We're done on that one. Okay. Questions on doing one like that? All right. So if we just want our probability of exactly some event, like exactly 2, like we had before, you use the standard binomial table. If we want to cover a range of values, we have to use the cumulative binomial table. And the cumulative binomial table gives us less than or equal to whatever number we look up. Okay. So what happens if that's not what we're asked? We want a range of values, but it's not asking us less than or equal. Let's look at another one here. Look at this one. Oh, no, there. This one. This one says, what is the probability that a salesperson gets a sale more than 2 times in 6 sales? So more than 2 times in 6 sales calls, if the probability that the salesperson gets a sale on any given call is only 50%. Okay. So no matter what we're looking for, we need N, T, and X. Here, how many trials are we doing? Here we're making 6 calls, so N is 6. We're calling a sale a success. So if we just make 1 call, what's the probability of success? 50%, right? It says a probability that the salesperson gets a sale on any given call is only 50%, so 0.5. And for X, we have to look for how many successes we're looking for. And this one says we want more than 2. More than 2. So for X, we want it to be greater than 2. So what are those outcomes in? More than 2 would be, since we were maxing out at 6, more than 2 would mean we want either 3, 4, 5, or 6 successes. Right? Those are the probabilities we want altogether. Okay. Unfortunately, our table doesn't give us that directly. We have to, a little bit more work we have to do, another little step. Our table will give us the probability of less than or equal to whatever we look up. But we've got a little trick we can do. And so let me kind of walk you through the thought process here. This is something where we didn't spend time on it in chapter 4, so we had to spend just a little bit more time on it here. And so we're making 6 calls. So the only possibility for the number of successes we could have, 0, 1, 2, 3, 4, 5, or 6. Those are the only possibilities. On this problem, we're looking for the probability of these outcomes, 3, 4, 5, or 6, more than 2. So we can call that X is greater than 2. The ones we have left over, 2, 1, 0, what could we call that? Yeah, we could call it 2 or less, right, or less than or equal to 2. So this probability, the ones we don't want, we can look up in our table, okay, because it's less than or equal to. And then we need some way to get to the part we want, this part. Well, we can do it because these are the only possibilities. So if we add all these probabilities up, what's it have to be? We add all the probabilities of 6, 5, 4, 3, 2, 1, and 0 up. What we got yet? The probability distribution, right? So if we add up all the probabilities, what's it have to equal? 1. Equal 1, right? There's no other possibilities, so you got to have a 100% chance if you add them all up. Right? So what we're saying is that if we add these 2 probabilities together, we got to get 1. Right? So what we can do, we want probability that X is greater than 2. So to find that, we can do 1 minus the probability that X is less than or equal to 2. Because this number we can look up in our table. We do 1 minus that number, and that'll give us the probability we want. This is as complicated as it gets. This is called, we're taking the complement. Okay? We do 1 minus the thing we don't want. Okay? That's taking a complement, so complement rule. Okay? So we can go to our table, have an N of 6, T was 0.5, and we're going to look up 2. Okay? Look up 2. So we'll go to our table here. on the cumulative table, right, because we're dealing with a range of values, n of 6, p is 0.5, and we're going to look up 2. So that's the probability of being less than or equal to 2. It's 0.3438. But that's not the answer we want on this, right? We don't want to know the probability of being less than or equal to 2. We want the probability of being greater than 2. So we do 1 minus this number. Okay, so 1 minus 0.3438. That came from the table. That will give us our answer, whatever that is. 1 minus 0.3438. This is 0.6562. So the probability of getting more than 2 cells is 0.6562, or a little over 65% if you're thinking about it. Questions on that one? That one's kind of had several things going on. You with me on it? Okay, all right. If you got that, you're in good shape. Don't get any harder. We do have one that's a little bit different. Yes, ma'am.
What if you found the one for 6 and found the one for 2? Did you subtract it and get the same answer? Like on the table?
Yes, because if you go to 6,
It would be 6
it'll be
to 0.
which is 1.
Yeah.
So that's what this is.
Oh.
Yeah, because if 6 to 0 would be everything, so that would be 1. So yeah, good thinking though. Yeah. Yeah. Think anything else? Okay. Got one more to do. It's not any harder. It is a little bit different. It's less. Look, you did. All right, this one says, suppose that 20% of the programs sold at the home games of a professional sports team during the course of one season contain a special discount coupon. If all 8 friends in your group bought programs at one game, what's the probability that at least half of your friends received the discount coupon? So this is binomial because we either get the coupon or we don't. So we need NP, and we need to figure something out about X. So how many programs are we going to end up with? Got to kind of read careful on this one. It doesn't just give it straight to us. It says we've got 8 friends in our group that are going to get a program, so we're going to end up with 8 programs. Up here it tells us 20% of the programs have the coupon. So if we're calling getting a coupon a success, P will be 0.2. Okay. And then how many coupons are we looking for? It says what's the probability that at least half of our friends get the coupon? So half of 8 would be 4. Right, so we want at least 4. And what does at least 4 mean? That means 4 or more, right, or greater than or equal to 4. Right, so 4, 5, 6, 7, or 8. Okay. So we want X to be greater than or equal to 4. So we can use the same trick as we did on the last one, because our table doesn't give us greater than or equal to, it gives us less than or equal to. So if you know, you got to flip the sign around to get what you want. And we're going to do the subtracting from 1 trick. Okay. Do the complement rule. So here we want probability that X is greater than or equal to 4. So to get that, we're going to do 1 minus something. And we want it to be something we can look up in our table. What's the opposite of greater than or equal to 4? Yeah, one way you can think about it is less than 4. And that's true, but it doesn't quite give us what we want because our table doesn't give us less than, it gives us less than or equal. But we got another way we can think about it here, because remember, our only choices are whole numbers, it's discrete data. All right, so getting less than 4 coupons, how many coupons would that be? That would be 3, 2, 1, or 0. So another way of saying less than 4 in this case is saying less than or equal to 3. Those two mean the same thing because we can't get like half of a coupon, right? So less than 4 is the same thing as less than or equal to 3. Now this we can look up in our table and then we can subtract. Okay. So let's see where we're on numbers. N of 8, P of 0.2. And we're going to look up, what are we going to look up? We're going to look up 3. Okay. If we go to the table, go into the cumulative binomial because we were dealing with a range of values. N was 8, P was 0.2, and we're going to look up 3 because we want less than or equal to 3. So there we get a probability of 0.9437. Hey, that's less than or equal to 3. That's not what we want on this problem. We have to subtract. Okay? So we'll do 1 minus 0.9437. From the table. And let's see what we get there. 1 minus 0.9437. Gives us 0.0563. Is our probability. Those are all the types you can have. You either have exactly equal to some number, or you could have greater than some number, greater than or equal to some number like we had here. If you just have less than some number, instead of less than or equal to, you just got to go down 1. Right? Like if it said we want the probability of x being less than 3, that means 2, 1, or 0. So you just go down to 2. Go down to 2. Questions on any of those? We had a long week. We were out Monday. It's supposed to be a short, easy week. Everybody's so tired for. I'm tired too. Well, that's it. Okay, that's all 5.2. So, if you don't have any questions, that's the end of class today. Okay? Yeah. So, go get some lunch or something. Okay? Where'd the sign up sheet make it to? Is it back there? Okay. I'll put the sign up sheet up front if you missed it. Thank you. Get it on your way out, and that's everything for test 1. Okay? Tuesday we'll review. Okay? We'll work through the practice test together on Tuesday.